Hello students, I am N. Sujana Kumari, Assistant Professor, Department of Mathematics, Annamacharya Institute of Technology and Sciences, Tirupati. In this video, I want to start off by introduction of calculus of residues and some definitions with examples. So here the unit name is calculus of residues. So first introduction. In complex analysis, we observe the functions which are analytic in a given region, but there are several functions which are not analytic at certain points of its domain. Specifically, in this unit, we will discuss such type of integral functions by using residue theorem, and it is also called Cauchy's residue theorem. And it is very powerful tool to evaluate line integrals of analytic functions over a closed curves. And the applications of Cauchy's residue theorem is to evaluate improper real integrals and infinite series as well. Now we go for some definitions. The first one, zeros of an analytic function. If a function f of z is analytic in a region R and f of z equal to 0 at a point z equal to a in R, then the function f of z is said to have a 0 at the point z equal to a. So which means an analytic function f of z equal to 0 at the point z equal to a in the region, then the point z equal to a is called 0 of the function. Now we observe order of zeros. So if f of a equal to 0 and f dash of a equal to 0, then the function f of z is said to have a 0 of first order at the point z equal to a. So observe the example, f of z equal to z minus 3. Here z equal to 3 is a 0 of order 1. So which means when we substitute z equal to 3 here, then f of a value, that is at a equal to 3, it is 0. Now we find out f dash of z for observing f dash of a value. So f dash of z equal to 1. Here f dash of z equal to 1. When we differentiate for f of z, that is z minus 3, we get the value, it is 1. Then we substitute z equal to 3 here. So it is not equal to 0. So here f of a equal to 0 and f dash of a is not equal to 0 at z equal to 3. Then z equal to 3 is a 0 of order 1. So next, if f of a equal to 0, f dash of a equal to 0 and f double dash of a not equal to 0, then z equal to a is called 0 of second order. Example, f of z equal to z minus 3 whole square. Here z minus 3 exists 2 times. So then z equal to 3 is a 0 of order 2. This is the simple way to finding the order of the 0, or otherwise we go through the conditions by using conditions. Our conditions are f of a equal to 0, f dash of a equal to 0, and f double dash of a not equal to 0. Then z equal to a is called 0 of second order. So in the same way, here we consider nth order of the 0. Nth order of the 0. So the conditions are f of a equal to 0, f dash of a equal to 0, and so on. F power n of a not equal to 0. F power n of a not equal to 0 means the nth derivative of f at z equal to a is not equal to 0. Then z equal to a is called 0 of nth order. Observe the example. F of z equal to z minus 4 whole power n, and z minus 4 have power n. So based on this power, we can denote order of the 0 easily. So here z equal to 4 is a 0 of order n, or otherwise we can observe conditions of the nth order 0. So to find zeros of f of z, we equate numerator to 0. So we find out if how to find zeros of the function, then we equate the numerator, we get zeros of the given function. Here we consider one example problem. So that is, find zeros of the function f of z equal to z minus 1 into z minus 2 whole power 4 by z. So f of z equal to z minus 1 into z minus 2 whole power 4 by z. So to obtain zeros of a function, we equate the numerator to 0. Then we get z equal to 1 and z minus z equal to 2. So here z equal to 1 and 2 are the zeros of the function. Now we observe order of the zeros. So here z equal to 1 exists only one time. So order of this 0 is 1, or otherwise it is called simple 0. And z minus 2 exists 4 times, then we say that z equal to 2 is a 0 of order 4. Then we discuss singularities of analytic function. So that is, different types of singularities are discussed here for the analytic functions or not analytic functions. The point z0 is called a singular point of f if f fails to be analytic at z0, but f is analytic at some point in every neighborhood of z0. So here we say that z0 is a singular point of f when it satisfies two conditions. Those are, f fails to be analytic at z0. So which means f is not analytic at z0, but f is analytic at some neighborhoods of z0. When we observe example here, to find singularities of the function, we equate the denominator to 0, then we get singularities of the function. So here the singularities of the function are z equal to 1 and z equal to 2. When we observe at these 2 points, the function is not analytic. So then z equal to 1 and z equal to 2 are called singular points. The next definition, isolated and non-isolated singular points. If Z equal to A is a singular point of f of z, and there is no other singularity within a small circle surrounding the point z equal to A, then z equal to A is called isolated singularity of the function f of z, otherwise non-isolated singular point. So which means z equal to A is a singular point of f of z, and there are no other singularities in between that point, that is in the surrounding small circle, in the small circle of the point z equal to A, then that type of points are called isolated singular points, otherwise those are called non-isolated singular points. For example, f of z equal to z plus 1 by z into z minus 2. Clearly, here z equal to 0 and z equal to 2 are the only singularities of the function f of z, and there is no other singularities of f of z in the neighborhood of z equal to 0 and z equal to 2. So hence z equal to 0 and z equal to 2 are the isolated singular points of f of z. So that means when we substitute z equal to 0 here, so our function is not analytic. And also when we substitute z equal to 2, then f of z is not analytic at z equal to 2. So these are the singular points of f of z. So when we observe the surrounding points of z equal to 0 and z equal to 2, that is the neighborhood points of z equal to 0 and z equal to 2. For example, if we consider z equal to 1, so that is the neighborhood point of z equal to 0 and also z equal to 2. So when we substitute z equal to 1 here, the function is analytic, the function is analytic at that point. So when we replace the remaining surrounding points, that is neighborhood points of z equal to 0 and z equal to 2, on that points the function is analytic. That means there is no other singularities in the surrounding of z equal to 0 and z equal to 2. Types of singularities. Let f of z be analytic within a domain D except at z equal to z naught, which is an isolated singular point. Then by the expansion of f of z by Lorentz theorem, we consider f of z by using the Lorentz theorem in terms of z minus z naught powers. So based on this Lorentz theorem expansion in the powers of z minus z naught, we observe different types of singularities. So in the f of z, we have two different parts. So these are, one is analytic part and the another one is principal part. So in the analytic part, we have z minus z naught positive powers. That is positive powers of z minus z naught expansion is called analytic part of f of z, and negative powers of z minus z naught is called principal part of f of z. So here we discuss types of singularities, especially based on the principal part of f of z. So in the principal part, there are no terms, then z equal to z naught is called removable singularity. That is, there are no terms in the principal part, then we call z equal to z naught is a removable singularity. And the next point, if an infinite number of terms in the principal part, then z equal to z naught is called essential singularity or isolated essential singularity. The third one, an infinite number of terms in the principal part, then z equal to z naught is called pole of a function. So here we discuss three types of singularities based on the principal part of the f of z. So in the principal part, there are no terms, then z equal to z naught is called removable singularity. If infinite number of terms in the principal part, then z equal to z naught is called essential singularity. Or if finite number of terms in the principal part, then z equal to z naught is called pole of a function. Now we go for order of a pole. If the principal part of f of z contains m number of terms at z equal to z naught, then z equal to z naught is called a pole of order m. So we observe in the previous point, if the finite number of terms exist in the principal part, then z equal to z naught is called a pole of a function. So here we observe finite number of terms. So on that finite number, here we consider m as m. So here there are m number of terms in the principal part, that m is called pole, order of the pole. So if m equal to 1, then the pole is called simple pole, or otherwise the pole of order 1. So to find poles of f of z, we equate the denominator to 0. See the example. F of z equal to e power z by z minus 1 into z minus 3 whole power 4. For finding poles of f of z, we equate the denominator to 0, that is z minus 1 into z minus 3 whole power 4 equal to 0. From that, we get z equal to 1 and z equal to 3. So observe, z equal to 1 and z equal to 3. These two are called poles of the function. If we observe order of the poles, z equal to 1 exists only one time, that is here 1 repeated only one time. So then z equal to 1 is a simple pole, and z equal to 3 repeated 4 times here, that is z minus 3 exists 4 times. So then z equal to 3 is a pole of order 4. So here the most important definition is residue of a function. So the coefficient of 1 by z minus a, the coefficient of 1 by z minus a in the expansion of f of z about the isolated singularity z equal to a is called the residue of f of z at that point. So 1 by z minus a means, that is negative power of z minus a at the isolated singular point z equal to a. So from this we consider, that is from principal part of the f of z, we consider residue of the function f of z. So the coefficient of 1 by z minus a, the coefficient of 1 by z minus a is called residue of f of z. The coefficient of 1 by z minus a in the expansion is called residue of f of z. So when we consider f of z in powers of z minus a, so this is positive powers of z minus a. This one is called analytic part, and this is negative powers of z minus a. This is called principal part. So based on the principal part, we consider residue of f of z. So here 1 by z minus a coefficient. So when we substitute n equal to 1 here, so we get a minus 1 into 1 by z minus a whole power 1. So we consider 1 by z minus a coefficient as residue, that is a minus 1. So a minus 1 is called residue of the function from Lorentz series. And we know that the coefficient a minus 1 is of the form, it is 1 by 2 pi I integral over c f of z dz. From this we get integral over c f of z dz equal to 2 pi I into residue of f of z at the isolated singular point z equal to a, and where c is a closed curve containing the point z equal to a, and f of z is analytic within and on a closed curve C. Next, formula for residues at poles. The first one, residue at a simple pole. If f of z has a simple pole, that is pole of order 1 at z equal to a, then we can find residue at the simple pole by using this formula, that is residue f of z at z equal to a is equal to limit z tends to a z minus a into f of z. So this is the residue at a simple pole, and this is also another form for finding residue at a simple pole. If f of z is of the form p of z by q of z, then we can find residue at simple pole by using residue f of z at z equal to a equal to p of a by q dash of a. So third point, residue of f of z at pole of order m. So if f of z has a pole of order m at z equal to a, then we can find residue at z equal to a by using residue of f of z at z equal to a equal to 1 by m minus 1 factorial limit z tends to a of d power m minus 1 by dz power m minus 1 of z minus a whole power m into f of z. So this is the formula for finding residue of f of z at pole of order m. And the fourth point, residue at infinity. How to find residue at infinity? So if f of z has an isolated singularity at z equal to infinity, then we are using residue formula, that is residue f of z at z equal to infinity equal to limit z tends to infinity minus z into f of z. So this is the one of the formula for finding residue at infinity, and the another one is from the Lorentz series expansion. So we know that from the Lorentz series expansion, the coefficient of 1 by z minus a is called residue of the function at z equal to a. But here we find residue at infinity. So because of that, we consider minus of coefficient of 1 by z in the expansion of f of z as a residue. So these are the some basic definitions of calculus of residues. Now we will discuss in the next lecture some examples on these definitions. Thank you.